Hello, everybody, and here's the week 2 of our online instruction surrounding Parabolae. I guess I shouldn't give that up yet, because here we have your do now. Just go ahead and do it. It's a repeat of what we did last week, circles, all that stuff. Oh, sorry, pause, do it, and now resume. And now we have all of the answers right there. Check your answers. When you see SQRT, when I wrote this in the program that I used, I couldn't get a radical on there, so oops. There was the assignment, but you already went over the assignment. Here we go. We are still on section 9.1. It is another conic section. So last time we talked about circles. That was week 1. Today, we are going to talk about Parabolae. That is week 2. So Parabolae, just in case you're really annoyed with me for saying it like that, that is the pluralized version of parabola. So just as a reminder here is the standard form of an equation of a circle, although not really that important. And now we are going to talk about Parabolae. Now, I will point out, if you were to take a cone and you were to slice through that cone at an angle so that you do not intersect two sides of that cone, you would get a parabola. So just to be clear, I have my cone right here. This guy right here, this slice on the cone is the parabola slice. So you can see there's the shape of the parabola, and I can hold it any way that I want. And that's important because you guys talked about Parabolae in what was it called? Algebra 2, I believe, when you were talking about certain stuff there. So since you've already talked about, or you already know what a parabola is, write a definition of a parabola. Seriously, take a couple minutes, and a neighbor, just go out. No, don't go out and ask a neighbor what a parabola is. That would be bad. But just write down a definition. If you're wrong, whatever, we'll fix it. And then pause, and then I'll just write down some things that I think of. I think of it's U-shaped. It's involving quadratics. You know, like x squared, that kind of stuff. Trying to think of it's curvy. It extends infinitely in one direction. Unlike a circle that extends infinitely in one direction. Those are just things that I can think of off the top of my head. It really kind of stinks that I can't get interaction with you guys on this. Because a lot of times, you people come up with some great stuff for me to put down, and I just don't know what you're thinking, so whatever. So here's the thing. Parabolae can be oriented in multiple directions. I know in the past, sometimes I've had people say it goes up or goes down depending on what the a value is that you learned in Algebra 2. But Parabolae can be oriented up, down, sideways. There are so many different things in the technical definition. We need a definition better than what you got in Algebra 2. So the definition of a parabola, and this you would probably want to write down. It is directly out of your book. A parabola is the set of all points, x, y, in a plane that are equidistant from a fixed line. That's called the directrix, and a fixed point. That is called the focus. That is not on the directrix. The midpoint between the focus and the directrix is the vertex, and the line passing through the focus and the vertex is the axis of the parabola. So just real quick, vocab words: parabola, directrix, focus, vertex, and axis. Pause if you need to write that down, and then resume here in just a second. You can see we actually have pictures down here. There's another word in here. It is called the latus rectum. I use the latus rectum to get the good openness of the parabola. I will show you how that comes up. But the latus rectum is perpendicular to the axis You may remember it from Algebra 2 as being called the axis of symmetry. Remember, parabolae are symmetric. Oh, man, that's another word that pops up whenever I have people brainstorm on words about parabolae. It has one axis of symmetry versus a circle that has infinite axes of symmetry. But the latus rectum, again, is perpendicular to the axis of symmetry, and it runs through the focus. That's important. Well, that's important because, again, that's how I figure out how wide the parabola is. And here's another one over here. It's got some H's, K's, all that stuff, which should be familiar. I mean, we used H's and K's for circles, so yeah, conic sections. You're going to see H's and K's out the yin-yang. So here are the standard equations of a parabola. We are only going with two orientations today. We are going with a vertical orientation or a horizontal orientation. In case you don't know what vertical means, it means like this, uppy, downy. Horizontal means lefty, righty. If you don't know that, you should probably write it down. So the standard form of the equation of a parabola with the vertex of HK, important to note that the vertex is the important point here, and we refer to that as h comma k, is as follows. For a vertical axis, you have the quantity of x minus h squared is equal to 4p times the quantity of y minus k, where p is not equal to 0. Vertical axis with a directrix at y equals k minus p. For a horizontal axis, you have the quantity of y minus k squared equals 4p times quantity of x minus h, where p cannot equal 0. That's a horizontal axis with the directrix at x equals h minus p. I don't personally have these memorized. I actually have to read them every single time to remember what they even say. I have a different way of finding where my directrix is and where my focus is. The focus lies on the axis p units, and that is a directed distance from the vertex. If the vertex is at the origin 0, 0, the equation takes one of the following forms. For vertical axis, it's x squared equals 4py, and y squared equals 4px. I will point out that the vertical or the horizontal standard forms of the equation look almost identical. The only difference is, for a vertical axis, the x variable is going to be squared. For a horizontal axis, the y variable is going to be squared. The easy way to remember this is just remembering what you learned in Algebra 2. Anytime you graphed a parabola, you had x being squared, and anytime you graphed a parabola in Algebra 2, because we were only dealing in functions, your x had to be the squared one. So that's the way that I remember it. But again, have those in your notes. You will need them. Oh boy! Oh, pictures, pictures, pictures. I personally would probably draw these pictures. They're on page 663 in case you can't see too well here. I'm just going to point out some things here. This is a parabola that opens to the right. On our last page, we actually had a definition of what P was. P is the directed distance from the vertex to the focus. So here, that distance is P. And since it's going to the right, this is where P is greater than 0. Hey, look, it says it right there. I will also point out that since every point on the parabola is equidistant from the focus and the directrix, this distance right here is actually the opposite of P. So that distance, that right there, is the same as that right there, except in the other direction. That's how I determine where my directrix is. Now here, we have our P right here. And in this case, since going from the vertex to the focus, you travel left, P is less than 0. And still, this distance right here is the opposite of P. I will point out, since I'm using the negative here, it's the opposite of a negative, so it's going to be positive there. Looking down here for the vertical orientations, we can actually see P right there. That P, since we start at the vertex and go up to the focus, goes up. That means P is greater than 0. And still we have this distance right here is the opposite of P. And last one, we have a downy parabola. We still have that distance right there as P. since we went down to go from the vertex to the focus, P is less than 0. And again, still, that is the opposite of P. Again, important pictures. I personally would make sure that I have this in my notes. All right, leave that up there for a second. You guys might want to write it down, and has an extra added bonus of me finding a straight edge. There we go. So the next thing that we're going to do is graph some parabolae. Let's graph a parabola or two. These are different from what you did last year. Am I right? Am I right? Of course I'm right. I'm always right. So let's just go with this one. And since I only have one graph here, I'm actually going to hop over to this lovely red graph paper that I have here. So, number one, what I have is, let's see, y equals 1/2 x squared. In order to graph this parabola, the first thing that I have to do is make sure that it is in standard form. And it is not in standard form. The problem that I see here is when I'm in standard form, actually, since there's no pluses or minuses off of the y or the x, I know that my vertex is at the origin. And when I look at these two standard forms down here, I see that the x squared has to be by itself. So the first thing that I need to do is convert this. By multiplying by 2 on both sides, I'm going to get 2y is equal to x squared. Now again, I know that that is in one of these formats, either the vertical axis or the horizontal axis, because I've got x squared equals 4py or y squared equals 4px. Well, looking at my two options here, since the x squared is by itself, let's just flop this over here. X squared is equal to 2y. We've got the symmetric property of equality, so I can do that. Oh, hey, look, it's in the vertical axis. In the vertical axis form. Okay, yeah, that's what I was looking for. All right, so looking here, the things that I need to figure out in order to get a good graph of this, I need to find out where the vertex is. Again, since there are no pluses or minuses on the x or the y, I know that my vertex is at the origin. The only other information that I need to figure out is what P is. And P, looking again at the standard form of a parabola here, 4p is equal to the coefficient of y when we have a vertical axis and vertex at the origin. So here I have 4p is equal to the coefficient of y, or the coefficient of the linear, I guess I should say more accurately. So 4p is equal to 2. Divide by 4, I have 2/4. Okay, p is equal to 2/4, but I've been working with my son recently, and I've been telling him, simplify your fractions anytime. So you got p is equal to 1/2. Knowing this much, I can actually form a great graph of this parabola. Oh, let's, what orientation do we say here? So I'm also going to put down that it has a vertical axis, because that's important. We have to know that. So looking here, vertex at 0, 0. My P is 1/2. My P, remember, is the directed distance from the vertex to the focus. Well, here in this case, since I have a vertical axis, that means my focus must be up or down. Since P is positive, I know I'm going to go up. I don't feel like going to the half there, so I'm just going to use that trick of make every 2 boxes into 1 unit so that I can measure a little bit more accurately. Now remember, anytime you make your tick marks counting by 1, you don't actually have to put the numbers on there. If you're lazy like me, I shouldn't say lazy, I should say efficient. Okay, that took a minute. So now here, I know that my P, again, is 1/2. That means going from the vertex along the axis. Oh yeah, we have a vertical axis. You can, if you want to, draw in the vertical axis. I never do. So I go up to P. There's my focus. Those are two things that I want to see on your graphs. I want to see the vertex and the focus. Other things that I want to see the latus rectum. Not the latus rectum, sorry. Not the latus rectum. I want to see the directrix. And the directrix is going to be a line that is perpendicular to my vertex and equidistant from the, perpendicular to my axis of symmetry and equidistant from the vertex to the focus. So looking here, since my focus went up 1/2 unit, opposite of 1/2 unit, my directrix would be down 1/2 unit. Okay, look at that. I have my directrix. Now the only thing left for me to do is to draw the actual curvy part of the parabola. And the problem that I see here, I want to know, is it going to be a wide parabola or is it going to be a narrow parabola? And the way that I determine whether it's a wide or a narrow parabola is I use the latus rectum. One of those words that I said will come up a little bit later. The latus rectum, remember, is the distance from the focus perpendicular from the axis out to points on the parabola. The latus rectum happens to be twice p. So I see here, p is 1/2. The latus rectum is going to go out 1. So now I have 2 other points that are on the parabola. That allows me to get the better openness, a more accurate parabola on it. Boom. There we go. Once you guys pause the video, try out the second one. The y squared equals -6x. Pause it. Do it. Then resume, and I'm going to show you what we have here. So first things first, I'm looking at here, since no pluses or minuses on the x's and the y's, that means it's going to be vertex at the origin. So vertex at 0, 0. Notice how I'm using some scratch paper over here to make sure that I can actually, get a good graph. Yeah, you should too. So vertex at 0, 0. Let's see, what else can I see here? Oh, I can figure out the axis here. Since the y is being squared, I'm going to have a horizontal axis. I usually abbreviate it as h-axis, but since y'all are here, I'm going to put out the whole horizontal there. So here we had vertical. My axis is now going to be horizontal. Only other thing that I have is to find p. Now, since I have the quadratic term isolated already here, I know that 4p is equal to the coefficient of the linear term. So 4p is equal to -6. If 4p is equal to -6, divide by 4, I've got p is equal to -6/4. And we all remember from before that we want to simplify to -3/2. Yay! All right, cool. Let's get to graphing this. So now I see here, I have my vertex at my origin. Again, I'm counting out the halves, so I'm going to want to scale this 2 boxes to each tick mark. I hope I don't screw this up, because then I would have to start numbering these, and that's too many numbers for me to write down. Downsies. All right, cool. There we go. Now I can find my p. Remember, I have horizontal axis. Since I have a horizontal axis, I want to either be going to the right or to the left to find my focus. Well, here, I've got -3/2. If you don't know that negative means go left at this point, write it down. It's just common knowledge. So going to -3/2, each box is 1/2, so right here. There's my focus. Again, things that I want to see. I want to see your vertex. I want to see your focus. I want to see the latus rectum. Not the latus rectum. Why do I keep saying latus rectum? I mean directrix. I want to see the directrix. So the directrix here, since I went to the left 3/2 units to get to the focus, I'm going to the opposite of left. If you don't know what the opposite of left is, I don't know what to do with you. The directrix is going to be right 3/2 units. So let's draw in the directrix. So I would guess that the directrix would actually be at the equation of x equals 3/2. Not that you need to know that. at this point. So here we have, let's see, I've got my focus, I've got my vertex, I've got my directrix. The only other thing I need to know is how wide is the parabola. And again, the way that I do this, since my P is -3/2, my latus rectum is going to be twice -3/2. So twice -3/2 is going to be -3. And really, it doesn't matter whether I have negative or positive because I'm going to be going out either direction. So 1, 2, 3. There's a point. Down. 1, 2, and 3. And we can see it's going to be a much wider parabola than we had in the first one. There we go. Boom. All right. So normally if this was in class, I would give you guys like a few minutes to try to do these, but pause it and then we resume immediately. So like looking at x squared plus 8y. Well, it is not in the standard form. Oh, sorry, x squared plus 8y. Why did I forget the equals 0? Equals 0. It's not in the standard form because I have the x's and the y's on the same side of the equation. I want to get them isolated. So just subtracting 8y from both sides, I've got x squared is equal to -8y. I can now see that since the x is being squared, I have a vertical axis. Again, I'm just looking for three things. What's the orientation of the axis? Where's the vertex? And what is P? And I can get my graph from there. So the vertex is, well, since I've got no pluses or minuses off of the x or the y, that's in the fourth one, my vertex is automatically at L origin. Now, in order to find P, I look at the coefficient of the linear term. I've got 4P is equal to -8. Divide by quattro, I've got P is equal to, I hope nobody thinks of that as -8/4. It's just -2. -2 right there. Ooh, I should scroll up there a little bit so you guys can see it. So P equals -2. Again, I have enough to make my graph now. Let's see. Vertex at the origin. Oh, sweet. P is a nice whole number. So I don't actually have to mark any of my boxes. I'm just going to use each box as one unit. So looking here, P being -2 with a vertical axis. Well, if you don't know negative is down, write it down. You now know it, and you're expected to know it for the rest of your life. So there I've got my vertex, I've got my focus. Those are 2 units apart. That means my directrix. Hey, first time getting it right, or saying it correctly on the first try. There we go. So now I've got vertex, focus, directrix. Only thing left for me to do is to produce the curve. And the curve, again, the way that I like to figure out how open or closed it is to just go twice this distance perpendicular to the axis of symmetry. 1, 2, 3, 4. I guess I'm kind of skipping there, that I assume you guys know what 2 times 2 is. It is 4. And now I draw in my curve. Now I know some of you are probably jealous at how amazing my curves look in this problem. We're talking like 2 decades of practice on this. So just practice a couple decades and you'll get it right. Oh, fourth one. No, I was going to do it on here, but I don't feel like it. Okay, so fourth one, we've got y plus 1 squared plus 8 times the quantity of x plus 3 equals 0. So right away, I can see I've got pluses, I've got minuses. I know that this is not going to be vertexed at the origin. So first things first, I want to get it in standard form. So getting it into standard form, I have to make sure that it says quadratic isolated by itself. And to do that, I'm just going to subtract this 8 times the quantity of x minus 3, so minus 8 times the quantity of x plus 3. Do it on the same on the other side. I have quantity of y plus 1 squared is equal to -8 times the quantity of x plus 3. Okay. So a couple things. First off, it's really easy for me to tell what the orientation is here. Which one is being squared? Is the x or the y being squared? Since I look over here and I see y is being squared, I know automatically, again, just going back to this page, I see y being squared. It is a horizontal axis of symmetry. All right. To find the vertex, I do want to point out in the standard equation, the equation says y minus k and x minus h. Notice that the x sticks with the h and the y with the k, regardless of which orientation you're talking about here. So since I have that minus in there, I know that my vertex, what's being subtracted from x, it's going to be the opposite of that sign in there. So it's going to be -3, comma. Other one, we have what's being subtracted from y. So -3, -1 is my vertex. And the only thing left to do is to find p. Again, going back to the standard form of the equation, 4p is the coefficient of the linear junk here. So 4p is that -8. I got 4p equals -8. Divide by 4, that means p equals -2. And now I jump over to graphing. For graphing, I start with vertex. All right, everything's an integer, so I'm just going to use one box per unit. -3, -1. Got me a vertex. Next, I'm going to find me my focus. My focus is -2 units away from my vertex. Helps if I know my orientation. Ah, look at that. It's horizontal. So horizontal means lefty-righty. Negative means just lefty. So there, I've got my vertex, I've got my focus. Keeping in mind that the vertex is here, focus is here, I now need to draw my directrix. Directrix is going to be the opposite direction, same number of units. So it's going to be 2 units to the right and running perpendicular to my axis, so running vertically. And now, just to figure out the openness, I see distance from focus to vertex, from focus to vertex is 2 units. So twice 2 gives me 4. 1, 2, 3, 4. There's a point on my parabola. 2, 3, 4. There's another point on my parabola. Oop, messed up that one. This is why you should never use pen to do math. Using pen in math is a fool's errand. There we go. And there's 4 parabolae for us to draw. Stick that over to the side in case I need it later. Find the standard form of the equation of the parabola with vertex at the origin and focus at 0, 4. So here we are actually writing the equation. That's our other goal. Other than being able to graph parabolae, we also want to be able to write an equation for one. So whenever I do this, I actually need to draw a picture. So I see I've got vertex at the origin and a focus of 0, 4. This allows me to construct my equation, my parabola. So looking at this, just a rough sketch. I really don't care how accurate it is. No matter. Notice that I'm not even using my graph paper for this one. So look at my vertex at the origin. My focus is at 0, 4. So 0, 4 is just going to be up 4 units. The reason I do that is because right there is my P. My P here is the distance from my vertex to my focus. Notice how I went up to get to my focus? That means I'm going up. How far is 0, 0 to 0, 4? If you don't know that's 4 units, draw it on a piece of graph paper, count the boxes, you can see that it is 4 units. So P is equal to 4. I know that since I have the vertex at the origin, I'm going to be using one of these 2 equations. Only thing left is to figure out what's the orientation of the axis. Well, let's look. The axis runs between the vertex and the focus. What type of line do we draw when we connect these two? I'll tell you right now, it's a vertical axis. Oh, spell axis correctly. Thank you. Vertical axis. So I'm just going to dump all that into this thingy right here. So looking at this, let's see, I've got vertical axis, so x squared equals 4py, so x squared is equal to 4 times p is 4y, x squared is equal to 16y. Perfect. Done. You don't have to do anything more. You will notice if you look on my on the PDF of my flip chart, I actually solved this for y, and the only reason why you would want to do that is to be able to plug it into your calculator, and really all you have to do is, I'll just put it up here, divide by 16, and you can actually see it's not that difficult to do. You can now plug into your calculator y is equal to 1/16 x squared, or y is equal to x squared over 16. Either way you want to do that is fine by me. Or, I mean, those of you that have one of these amazing TI-84s, I kind of told you guys about the Conics app last video, but I forgot I didn't have my calculator up here, so I couldn't do that. If you go into applications, you can go down to Conics. You have all 4 different Conics sections right here. We're trying to graph a parabola, right? So you hit enter on parabola, and you can actually see, you can graph directly from here. So, I mean, looking at this, I've got my y minus k squared equals 4p minus times quantity of x minus h squared. That's for my horizontal orientation. In case you guys can't see it on that screen, it actually shows horizontal. Down here, it actually shows it's got a vertical axis. So that's one I want to use. My h and my k are just the coordinates of my vertex, so 0, 0. My p is, what was p again? 4? All right, cool. So I can actually graph that really easily on my graph. Not that you would ever want to make a graph of anything, right? All right, cool. Find the focus of the parabola. Good. Oh, I guess I should highlight the steps for doing this. Graph the vertex and the focus, determine the orientation, and then plug and check. Not too difficult. Find the focus of the parabola given by y is equal to -1/2 x squared minus x plus 1/2. Ooh, my goodness, I hate this one. This goes back to the completing the square that we did last video. So write it down. I'll lead you through it here. So if you are completing the square with a parabola, the first thing that you want to do is you want to get the loose term by itself. So move the loose term. That's this guy right here. You want to move the loose term so that it is with the linear part of the problem. So see how it's with the quadratic? We want to move it over here. So I'm going to have y, let's see, if I subtracted 1/2 from both sides, I'm just shifting over here so I have some more room. Y minus 1/2 is equal to -1/2 x squared minus x. Okay, cool. So I've moved the loose term. Next thing that I want to do, I want to clear out the fraction. Clearing out the fraction means get rid of this 1/2. While I'm getting rid of that 1/2, I'm going to want to get rid of that negative. To get rid of a 1/2, you're going to multiply by 2. To get rid of the negative, you multiply by -2. Multiply by -2 on one side, multiply by -2 on the other side, distribute the -2 over here. I've got -2y, negative times negative becomes plus, 2 times 1/2 becomes -2y plus 1 is equal to negative times negative gives me a positive, 2 times 1/2 gives me 1, so x squared, negative times negative gives me plus 2x. All right. Next thing we're going to do, we are going to complete the square. Completing the square we did last class. You take the linear term of the quadratic section, divide by 2, and square. So we take 2, divide by 2, we get 1. We square 1. We add 1 over here. I had to grab a different color so I can keep it color-coded for you guys. If I add this blue 1 over here, I got to add a blue 1 over here as well to maintain my equality. Now I have -2y plus 2 is equal to x squared plus 2x plus 1. This now becomes easily factorable because we completed the square. This becomes quantity of x plus 1 squared, just from reverse foiling. What I want to do while I'm factoring that trinomial, I want to factor the other side. So factor out, well, if you can't tell, there's a GCF here. There's a GCF here. And as long as you do this correctly, in this step, there will always be a GCF. This GCF is going to be 2, but even clearer, I want to use -2 because I want to make sure that the y becomes positive. So I'm going to factor out a -2. I got -2 times quantity of y minus 1. All right? Now, I tend to get a little bit bothered just in the sense that this is not in the same it's flipped from what the formula says. So I like to just put it as x plus 1 squared is equal to negative 2 times quantity of y minus 1. And that makes it a little bit easier for me to find out what h and k are, to find out what p is, and all that stuff, to figure out where the focus is, where the vertex is, all that stuff. So the vertex is going to be at h comma k. Again, I look over here and I see h is subtracted from the x and k is subtracted from the y. So the vertex, let's just put that all right here. Vertex is going to be at h. Well, looking here, I got h is equal to, what's being subtracted from x? Oh, it's negative 1. Over here, k is what's being subtracted from y. Oh, that's 1. So h comma k is going to be negative 1 comma 1. The other part that this is asking is to find, or well, the only thing this is asking is to find the focus. To find the focus, remember, the focus is p units away from the vertex. Well, if I know that my vertex is at negative 1, 1, that's right here. In order to find out what my focus is, I need to find out what p is. Well, again, this right here is 4p. So 4p is equal to negative 2. Divide by 4. We've got p is equal to negative 2/4, which again, we know from my yelling at my son, it is simplified, the best way to do it. So here, looking at this, what kind of axis do we have on this one? I got to know. I mean, it's a negative, so I'm either going to be going down or to the left. Oh, let's look over here. Since the x is being squared, I know this is a vertical axis. That means I have to go down 1/2 unit. Well, down 1/2 unit from negative 1, 1 is going to be down 1 on the y coordinate. That's going to be negative 1, 1/2. Short answer to your question, the focus is at negative 1, comma 1/2. Here's everything written out for you guys in case you want it. It is also on the PDF of the flip chart, running through the completing of the square here to find the focusing. Again, I use the graph, but you could also use those formulas that I said I never memorize where the focus is. All right. Find standard form of a parabola with vertex 1, 1 and focus at 2, 0. Okay. Oof. Man, I don't know if I can do this. Okay, so again, what I like to do is I like to draw a picture first and foremost. So the vertex is at 1, 0. The focus is at 2, 0. So looking at this, just drawing a rough sketch. Again, I don't care how accurate the sketch is. I see 1, 0. Okay, that's not really evenly spaced, but whatever. 1, 0 right there. Let's just label that as vertex so that we can remember it here. So vertex. The focus is at 2, 0. So 2, 0. Right here, focus. Well, actually, really quickly, I can see I have a horizontal axis, right? So horizontal axis means I want to be dealing with the y minus k squared equals 4p times quantity of x minus h squared. Well, we already have the vertex is h comma k, which is equal to 1, 0. So I know h is equal to 1, k is equal to 0. Only thing left is to find p. It's right here. Count. To go from 1, 0 to 2, 0, my p is going to be 1. All right? So looking here, I can just dump it right into the formula. I mean, I'm talking horizontal axis, so I'm just copying this off of the other page because I don't feel like throwing it in front of you guys again. Y minus k squared is equal to 4p times the quantity of x minus h. Okay, so let's just start dumping stuff in here. Y minus what's my k? K is 0. Squared is equal to 4 times what's my p? My p is 1. X minus what's my h? My h is 1. That's good enough, but again, we're not always reaching for good enough. We're always reaching higher. So let's just do this a little bit. Y minus 0 is just going to be y squared. I'm just cleaning it up a little bit. 4 times quantity of x minus 1. If I were you, that's where I would leave it. Again, if you have a TI-84, you can graph this and see, you can graph it in the Conics app is what I'm trying to say. If you don't have a TI-84, let's say you have a TI-83, you would have to solve for y. And looking at this, when I solve for y, I could just square root on both sides, so I'd have to do the plus or minus the square root on those. So yeah, there we go. Now, the last thing that I'm going to tell you guys is where we see parabolae. And I wish I could have, wish I didn't have this giant white box in front of here, because there's a nice picture on page 665 in your book that actually shows a curved reflector, is what we call it. It's a parabolic reflector, and it looks like this. We have a focus right here, and what's nice is there's something called the reflective property of parabolae, and anytime any let's just call it a signal bounces into the parabola, when it bounces in parallel to the axis of symmetry, it bounces off of the parabola and just goes right to the focus. Doesn't matter it's there, as long as the signals come in, and I'm saying signals, just some sort of thingy comes into the parabola and bounces off the parabola, it will reflect right into the focus. So looking here, it's going to bounce right into the focus. Again, look on page 665 to see this. Let me put that down in case some of you are more visual. Page 665. And what you actually can see here is the picture on page 665 is a little bit better. It actually looks like a cutaway of a satellite dish. Because a satellite dish, if you cut it right down the middle, it actually has a profile of a parabola. And the reason why you have a parabola for a satellite dish, you have all these signals coming in from space, and they bounce off of, they're really weak signals. And when they bounce off the parabola, they can go right here. This thing right here, if you have never looked at a satellite dish, go out in your neighborhood and walk safely distanced from everybody that you see and find a satellite dish. And look, you're going to see a little antenna hanging out over the satellite dish. It's just attached to an arm right there. And that's what's actually receiving the signals, because these signals are weak. But when they bounce off the parabola, you get many, many, many weak signals bounced right at that focus, and the signals become strong. When you have many weak things together, they become strong. Same thing if you've ever seen one of those spy shows with somebody holding up one of those like a cone that they're aiming at people, and they have headphones on, they're trying to listen to people. And this is the reflective property of the parabola. It's the tangent line to a parabola at a point P makes equal angles with the two lines. What that is saying is just whenever you bounce off of a parabola, bounce off the parabola, you end up right at the focus, which is why we see parabolae in certain applications. This is going to be posted on the Google Classroom, but there you go. There's the assignment. And it was fun. Let's do this again next week.